Yo, yo, yo. What's up, everybody? Welcome back. Today we are doing interrupt handling on the Raspberry Pi Pico with no Raspberry Pi Pico SDK. The context here is that we've kind of been on this journey to do some low-level programming. We started with like wanting to reverse engineer the firmware on the Xbox controller I was working with. We've kind of pivoted a little bit into the idea that we want to make our own Xbox controller. We're taking a little bit of inspiration from this open source controller. I just Google open source controller, clicked the first link, and found that there's an example here of a PCB where they just solder a Raspberry Pi Pico on top. That sounds kind of nice. That sounds kind of like a cool approach, something that will work for us. And so we are kind of working on making a Raspberry Pi spit out controller data over USB, right? So we have been looking a little bit today at what it takes to get the USB controller on this guy functioning, correctly. And what we have ended up seeing is that, part of the communication flow between the host and the device is that the Raspberry Pi on him in this like SoC system on a chip RP2040, he's got like a little USB controller in him, right? And that USB controller, when data is ready, is going to be like, boom, excuse me, CPU, sir, stop what you're doing. I've got some data ready for you. And so we need to be able to respond to that request from the USB controller, which means that we're going to have to set up, some sort of interrupt handlers, which we haven't done before. We haven't done that before at all. So I think as of right now, if an interrupt fires, I don't really know what happens. Probably nothing, I think. I don't actually know. But I think that what we want to do is we want to figure out how to do interrupt handling in general on this guy. And so the plan is to try to initialize some sort of interrupt table, right? Somewhere on this processor, he's going to say, yo, I got interrupt number 15. Now what? Right? And that now what is, I think, going to be like jump to this specific address in my just jump to this address where I have put some code that will handle that interrupt as necessary. Then we're going to try to like trigger some interrupts. I think that we can just inject a SVC call that as we saw in this ARM v6m specification, which is the ARM profile, I guess, that our Cortex M0 Plus that's in the Raspberry Pi or in the RP2040, this is him. And they're saying in here that there is a exception that can be triggered that is just like type SVC and then we will go here, right? So if we get that hooked up correctly, then we'll have known that we've like hooked up the interrupt vector table correctly. And then we have to play with interrupt handling to figure out like how do we like make sure that these exceptions are cleared? How do we get back to normal execution context, right? Like I know that on x86 you have this like iret command that says like, hey, interrupts, when we interrupted, we knew that we were coming into this context, so we put a bunch of stuff on the stack. All of the registers that you were using in your previous function, those are all boom, stored right here. iret is like your special interrupt return way of saying, okay, go back to where you were, and then also like go back from like whatever privilege level we're in now, and put all of the registers back where they're supposed to be, that type of shit. I don't think that that's the same here. But maybe it is. Oh, nice. Gray Hatter's just noted B1.5.8 in here is exception return behavior, which we will need to look at. Let's just be 1.5.8. I'm curious now. Nice. Interesting. Cool. Okay. So let's get moving and just kind of see where the day takes us. So we have been kind of jumping around. We've been using a few references here. One of them is the Raspberry Pi, the RP2040 datasheet, which is the datasheet for this system on a chip. And he kind of says some things about exception handling in here. He says that we have the processor's like memory mapped registers live somewhere. I can't remember where. They're somewhere. And that the VTOR there is this like vector table offset register that is offset from this guy. So M0 plus lives here at this memory. You just write to this memory address and you start writing to some registers. And here we want to write to the vector table offset to say, hey, CPU, something happens, jump here. We were looking at as well the CRT0 of the SDK, which I guess we don't have open right now. But in here, RP2 common, I think, CRT0.s, probably this guy. So this is kind of like when the processor boots, it runs some initialization code. At some point, you get into your function int main void. When you're using the SDK, they initialize the stuff before main in this CRT0 function. We are not using SDK, but we're using it for documentation and inspiration is something that I'm like totally okay with doing. And in here, what they do is they basically create this global variable vectors, and in here they just start slamming all of the different interrupt vectors that they might have, and then somewhere they call down here, they like stick the vectors thing into R0, and then they slap the content of R0 into R1, where they take this as like the VTOR spot, right? So we have some confirmation that there's this register on the CPU. It points to an address. When it interrupts, it jumps to that address offset by some amount, the interrupt number, and we just have to implement those functions. Or like we have to just put a function there and implement it. I think this also lines up with what we saw in the ARM spec here. I think they were talking about the vector table here, where they say this contains the initialization for the stack pointer and the entry point addresses for all exception handlers. So something that we read in Happy Hour as well is that the interrupt handler on the ARM processors will automatically switch your stacks, right? So you'll be like in a function. You'll be in some function and you'll have like memory, right? And you'll like enter your function with your like stack pointer set here. You'll like push some stuff onto the stack. And typically what happens is then you exit the function, you reset the stack pointer back to here and move on. Or if you like call a new function, your stack pointer will be here, and then your new functions stuff will be in here. They're kind of saying like, hey, when you interrupt, you're just going to be like, I have interrupt stack pointer at like some address 1, 2, 3, 4, right? And when the interrupt fires, I will like just take this stack pointer and like put him over here, right? So where here is like defined by the first entry in the stack pointer, then the exception table, I think. So I think step 1 here is creating an exception table. And I guess we think we need some interrupt that we're going to play with, right? And I want that to be something that we can just trigger. So we saw SVC here is like an instruction we can trigger that will go to something. So we want the exception number 11 to be initialized to our handler, and then everything else to just probably be zeroed out, I think. I don't know if it said this, but I'm assuming that if you have 0 in the exception handler slot, that it just won't do anything. But I don't know if it says that. I'm just kind of like assuming that based off of the implementation of the Raspberry Pi version of this thing. So in here, they have this like, if IRQ decal, right? So they say, hey, if number 0 is less than the number of IRQs that we support, call decal ISR on this thing. So they have like ISR IRQ 0. They call decal ISR. Decal ISR just creates like a weak label for something where it won't be defined otherwise. So I assume that in that case, if the user doesn't define a function, that this weak label just gets the address of 0 and then there's nowhere to jump to. So either I guess in these cases when interrupts fires and we haven't declared anything, it just like blows the fuck up, or they have something special at 0, or it just resets the processor because the beginning of the processor you boot at, maybe like boot ROM 1 starts at 0, or 0 just doesn't do anything. I guess we can kind of try that actually. Maybe that's the actual step 1. Is let's just try triggering an interrupt that we don't handle and see what fucking happens. That seems kind of reasonable. So how do we want to do this? I guess we do like, do we have any assembly files in here? No, but we can make one. We can just say like functions ASM, right? And we can like make a text section and be like global crash me, right? And then we're like crash me calls SVC, right? I guess it's not .asm, it's supposed to be .s. And then I guess it's fine. We can just probably leave it like that. And then we can like add that as like a thing that we want to compile. Functions.s, the classic. And then in main, can we just say like pub extern function crash me? Or there's an external function crash me, and we're just like, crash me, please, sir? I think that will do what I want. I'm not really 100% sure, but we'll see. No, he's mad because, what? Too few operands. SVC instruction arm. Maybe it's actually just like in here. Change supervisor call. Maybe this isn't what I want, but whatever. Okay, let's just slap a 0 on there and see what happens. Functions.s. I don't actually know what this thing does. You know, which probably is not helping. Okay, and then maybe right before that thing, before we call crash me, let's insert a breakpoint. And then we can kind of see what happens. Okay. Well, I guess we didn't try to return from this thing, which probably is not helping us at all. Can we actually, maybe we like just inspect state at that point and just take a little peek? So we're like step instruction, and then can we like info registers here? Like, I think that we saw on exception exit, we should just jump anywhere. Our link register here is 2013, which might be where we were, to be honest. Could be, because the breakpoint was at OC. Let's try just slapping a BXLR on here and see what happens. Because they did say just branch anywhere, I think. Maybe. We'll just breakpoint after and see if we hit that. Have to go, but learned a lot. The time was here. Cheers. Happy Friday. Happy Friday. Okay. So we are not exiting the exception. Hold on. Sorry. Monitor reset init. Step instruction, or continue. Step instruction. Okay. So we never make it out of this thing. Okay. So I mean, we haven't set up an exception handler, which makes sense. But it does seem like we are, at the very least, calling that instruction and some weird shit's happening, right? So let's just kind of hope that if we initialize the exception handler correctly, that we'll start seeing some behavior that we want to see. Let's do that. So what do we want to do? We need some like memory somewhere that we can just point the exception handler to, right? So can we just define that in Zig? Maybe. So they said somewhere that we have all other entries have bit 0 set to 1 because this defines the EPSRT bit on accepted entry. Okay, so I think that we just start slapping some values in here. So we need the stack pointer that we want to use. Which I guess is gonna be kind of the bottom end of the stack, probably. If I remember correctly, we have like SRAM is like kind of like this whole thing. And we have like, this is just some set of addresses, if I remember correctly. So we have SRAM, we have RAM starting at here with 256K of length. So we have 0x2 out, 1, 2, 3, 4 up here. And then at the top, we have this plus 256. Then I think 256K. Then on boot, we copy paste the bootloader into the very end of RAM, and then the stack pointer gets set here, right? Then in our bootloader, we copy code, like the rest of the executable down here. And then we need to pick somewhere that is a sane stack pointer location for the interrupt, right? So clearly like anywhere here is not good. But maybe here is okay, because once we're like the bootloader is done, we don't need it anymore. So maybe this is like a 256 byte stack is maybe enough for the interrupt handler. That seems kind of crazy. We could maybe push the stack pointer, our initial stack pointer down before we get into main so that we have more space there. That seems kind of reasonable. So we could look at our bootloader in here and just like before we jump into main or start, we just drop the stack pointer down. And then we leave ourselves like maybe like, I don't know, 256 bytes is small, but like 1K maybe is fine. Can we just like increment the stack pointer? Can we just like add, subtract? Because we're starting at big number and going to small number. So subtract immediate from stack pointer sounds hype. So we just like subtract 1K from the stack pointer. Oh, and then this should still, everyone should still be happy here. So let's just run. I guess let's check first before we do this that what our stack pointer is. We can like info registers stack pointer. So this is his value before. And then if we subtract a bunch of shit from him, he doesn't like that. Why? Invalid operand. Do I need to put a pound sign here for immediate value? Really? Maybe the immediate value is too big? Yeah. Okay. So info registers stack pointer. This is now D28 when before it was E28. So that makes sense. We can subtract up to, 256 bytes in an immediate value, but I think that we can't put a bigger number in there. So I think that if we want to do a subtraction from another register, we do this. I think we go like, I think we need to load like we load R0 with an immediate value of 1, 2, 3, 4. Then we sub from the stack pointer R0, sorry, 1, 0, 2, 4. Then we call start. He doesn't like that. Sub S. My bad. Which he still doesn't like. Let's just double check. If I don't do this, I do like R0, R0, R0. Does that work? Yeah, that works fine. So subtracting stack pointer R0, he doesn't like. Maybe stack pointer is special. It could be. And maybe we're not allowed to subtract from the stack pointer with another register. What about number 1024? I think that you can't do that because... Oh, sorry. This should be not 0x, huh? That's a pretty good point. Yeah, I think it's just that this is too big, right? You can do 256. He's... Oh, it's sub here. So sub stack pointer 256 is fine. But if I go to 257, I assume this won't compile anymore. Yeah. Because you can't encode more than 8 bits into an immediate, which is annoying. Yeah, maybe I can't... I wonder if I just can't do this. So that's not okay, right? But can I do this? R0? Yeah, he doesn't like that either. I wonder if you can do like... yeah, we can only do R0 to R7 here. Just do sub 4 times. You know, that does kind of feel like where this is going, huh? I mean, that works, so fine. So now our stack pointer is at 1A28, which is much lower, I believe, than wherever the fuck we were before. Before we were at 1D28, or 1E28 even. Right, so we've gone down by that much. That makes sense. Okay, so now we've allocated some room for 1K stacks. Let's say make room for 1K stack at end of RAM for interrupts. And then actually, note that the bootloader takes up the last 256 bytes. So I guess we just need to get our stack pointer to a specific value. Can we just like set the stack pointer directly? Can we like just move into like, hear me out here. Can we just like move stack pointer 5? No. What about like load? Oh, we can do load something directly into the stack pointer. So we could do load register stack pointer with RAM, like SRAM base plus 256K minus 1K, right? Something like this. Do we have SRAM base in here? Yeah, we do. So we could probably do something like this, plus 255 times 1024. Is that right? Oh, this is stack pointer relative, not load into the stack pointer. God damn it. Can I not just like set the stack pointer directly arm set stack pointer to register. Arm v6. I guess maybe in this document, this arm reference, do we have like instructions? Stack pointer. I think we're in unified assembler language. Data processing. Load and store, blah, blah, blah. Is the stack pointer just R13? I feel like I have seen that, huh? So maybe I am just supposed to do, like, instead of writing stack pointer directly here, you're saying I could kind of just, like, slap an R13 in here? Nah, he still is unhappy with that. Oh, here. R13 instruction support in ARM v6m is restricted to the following. Move. And adjusting R13 up or down by multiple of its alignment. Oh, so I can do add plus register. So I can set it to 0. And then I can add. So I can load register 0 with this and then add that to the stack pointer. Right? I think that's what they're saying. Am I fucking stupid? R13? Oh, is the move only from another register? Am I fucking crazy? Is that what it said? It says that I should be able to use stack pointer as the destination. Maybe it's move with an S? I know that sometimes for an S. Yeah, he doesn't like that. Operand must be in a range 0 to 7, which he doesn't. Oh, here we go. Oh, we can move from. Wait, am I stupid? Move into R0. Am I just using the move instruction wrong? Yeah, I am. How do I... Oh, it's move S? Oh, I see. And we don't have move S on the stack pointer. So we just do move R0 SP from R0. That was allowed, right? Did we try that? Ah, nice. So that works. So here we just say compute into R0, then slap that shit into the stack pointer, then set R0 to start into another. Okay, cool. So let's just make sure that our stack pointer is sane. So here we have this, which looks like some whole number back from the maximum value. 256 times 1024 in hex. And then 1023. Yeah, that looks about right, because I assume that the stack pointer has been incremented a little bit by our function as well, right? So if we put a breakpoint on here, we should see this guy have, info registers stack pointer. That doesn't look like what I want. Am I crazy? Info registers stack pointer. Okay, I mean, that looks right. Am I just stupid? 2004000 minus 250. Oh, times. Am I minus 256, right? Which means that this is times 1023. Yeah, there we go. That makes more sense. Not that any of this matters. There we go. That's a number that looks like what I want. I think, right? We take the max value of RAM, 0x2004000 minus 1024. Yeah, there we go. Oh, I'm just a dumbass and it was right the whole time. It was right the whole time. I just can't do math. Yeah, okay. So if we take the maximum value of RAM, we subtract 1K, we get this number. So make 1K room stack at the end for interrupts. Note that this overwrites the boot loader. But stack will not be touched until we are in start, where the bootloader does not matter anymore. Okay, there, that seems kind of okay. Cool. That seems reasonable. So now, when we create our interrupt table, we can say that our... I guess maybe we should just define that somewhere. Because we're just going to have to do this same math again on Zig side. But we'll handle that later. So I guess we'll just say fix me dedupe with whatever. Functions.s is what we called it. No, boot.s. There we go. Are you sure you don't want to reserve for heap space? Yeah, fuck it. I think that I can make my heap grow up from the bottom. Like if we have this, we can kind of make heap here. And then eventually the heap and stack will just collide. But I think that this is how I would do it if I wanted to do heap. And that way it doesn't really change anything. Okay. So we'll say this is the interrupt stack. Oh, this actually just starts at the SRAM base plus 256 times 1024, right? We just put it at the very end of RAM. I think that's right. 1234, 1234. Yeah, sure. Or what we know is for 200400, I think. Parenthesis X. I fucked this up. Yeah, just 2004. 2004. Boom. So this is like end of RAM. There we go. Cool. Cool. So we need to put this somewhere, right? So we need some, data where we have like U32s, a bunch of these guys. Interact, vector, interrupt vector table. And I think this is just like however many of these things they want. How many do they want? Where were we in like B something exception model? Here we go, vector table. So how many of these are there? 16 plus n, and I think we have 16 external interrupts. I think. Interrupt. 26 external interrupts. So 16 plus 26 is 42. I guess. Can we do like a little like splat 0? But then we want to set the values of the stack and stuff. So can we actually do like function make interrupt table? We'll return interrupt table. And then here we like define interrupt table as 42 U32s or something. And then here we're like, our table is going to be an interrupt table, a splatted 0. Okay. And then here we're going to set table 13 is equal to like SVC handler. Int from pointer. And here we have like SVC handler. Now, do we have to be careful about this guy generating the correct preamble and shit? Maybe. Let's just see what happens if we hit breakpoint in here. Oh, I think that crashes the processor. Maybe not. We'll see. And then we need table 0 to equal interrupt stack. SVC handler is a pointer. What if I put an ampersand in front of it? This doesn't compile probably, and we also didn't run this, so this needs to be make interrupt table like this. Redundant comp time, and then somewhere we need to initialize the interrupt table, right? So here we need to be like init interrupt. What do we want to call this? Like we might want to use this as like, we have this like register set up, right? We have like reset register, exhaust registers, clock registers, right? So I guess like the interrupt handler registers might be like that, but I think that the like the internal processor registers on the RP2040, sorry, the registers that are memory mapped into the from the Cortex 0 Plus are different than all of the rest of the external RP2040 memory mapped stuff, I think. So I don't know if we want to use the same interrupts or the same like memory mapping subsystem. Skimming, looking for something about memory mapping. Okay, we have memory. Okay. So he's saying I only support word size accesses in this range. So if our processor stuff is in that range from starting with a D to starting with an F, those are the spots. So it looks like this should use the same subsystem, I think. Okay, so that means that, is this why they use memory barriers? Maybe. Good question. I would think no. My guess is no, but I don't know why they use the memory barriers. So anything that you ask, I would guess no, and then I'd be wrong 1 out of n times. Right? So Is Zig gonna generate a line for function pointers? Who knows? I hope so. I would assume it has to, but I could be wrong. Okay, so we have our like big JSON blob of registers. And we have this abstraction where these register definitions turn into like Zig classes that wrap U32s because we need to make sure that we're doing U32 reads and writes. And so here we just kind of have like an abstraction that gives us like nice little field name entries and stuff that still wrap a U32 so that we don't do like narrow writes by mistake. So here we should be able to be like Cortex M0 plus Vitor, I guess is a good name for the register here. And here, I guess we need to say, hey, we are writing to bits 31 to 8. So we have like offs, I guess, is what we'll call it. And he is in the range of 8 to 31. These are the bits that we're allowed to write here. And if we run Zig build now, what should happen is our register file here should now end up with a class, Cortex M0 plus Vitor, who has, a bunch of helpers on him. But the important thing here is that we can write the offset value. So we should be able to be like, I guess we need to specify that register lives somewhere. So we could do, we have Cortex M0 plus is a structure. And in here, he has Vitor, which is a Cortex M0 plus registers Cortex M0 plus Vitor. And we have to initialize this thing. So this is going to be like initialized with base plus whatever offset they gave us here, this guy. Boom. And then we need to set the base to this. Boom. Simple. So now we should be able to be like, here, let's just take that Vitor guy and modify him with, I think, what do we do here? It's like all. And then here we specify offset as the address of our interrupt vector table. Like this. So he's expecting a U24, found a pointer. So this is kind of interesting. I wonder if this will work. Or, like, this is strange to me. The fact that this needs to be... Oh, this is... I don't know if this is saying that we can only specify addresses that are in the low 24 bits, or if it's something else. Unable to evaluate comp time expression. Oh yeah, true. I forgot this is not going to work. But can we do this instead? I think this will work. Expected U24 we found U size, so then we int cast here. And I think it should be fine. Unable to evaluate comp time expression. Is this because the SVC handler doesn't know its address at comp time? This is confusing to me. Low bytes need to be 0, won't be? I guess we'll find out. Okay, let's just do a stupid. What if we just slap a 1, 2, 3, 4 in here for now? We're hoping to see that when we issue our SVC instruction, shit falls apart. Interesting. Okay, so this is not behaving the way I expect at all. So I think it's probably because we're trying to read from this guy because we're trying to not touch the reserve bits here. And I think that's fucking it up. I think it might just be that we're supposed to write directly because that's what we saw them do in the SDK, I think. Right? We saw them just like slap R0 into that guy, I think. Where was it? Here. Yeah, they literally just like, oh, well, it depends on what this does. Like, what the fuck is this? Load multiple increment after a full decreasing. Load multiple, dude. Increment after loads multiple registers from consecutive memory locations using an address from a base register. So they put R0 as the dereferenced value of they store the old vector table here, I think. I need to line 256 if I want the pointer to be 0. Yeah, I know. I agree. But we're not there yet. We're not there yet. So he says load multiple increment adds multiple registers from consecutive memory locations using an address from a base register. The sequential memory locations start at this address, and the address above the last of those locations is written back to the base register when the base register is not part of the register list. Okay. So he's writing R1 and R2 to the register table. And then this feels backwards to me. Like this is dereferencing the V table offset, I think. So he's saying like put the address of the vector table in register 1, then store the value of R0 over there. Got it. Then put R1 and R2 into that spot, which is confusing. Load from consecutive memory addresses using... Oh, he's loading the stack pointer and the first interrupt value into R1 and R2, I guess. Then doing something else. Oh yeah, you're also right about the store dereference thing being wrong. Like my interpretation being wrong. What is store here? God damn it. Yeah, so this is confusing. So he's taking the V table, putting it in R1. Then like, why is he ever putting this stuff into R0 if he's immediately clobbering it here? Am I crazy? What's the point of this then? right? He's saying take the vector's value, put him in R0. Then he's just like, womp womp. Okay, now take this and put it in R0. That doesn't make sense. Does not make sense. Confusing. Okay, I'm just gonna ignore all of this and do something stupid. What if we did that instead? So we're just like, what if we're just like, Vitor, just fucking write that shit with this guy directly. Int from pointer. Right, let's just do that. Okay, so we're like, now that writes successfully, which is hype. Okay. Then we get to 336, and then we fall over. So 336 is here. Then we try crash me, shit falls over. Right, so I would be interested to know if we start stepping by instruction here, what happens now? So we go into crash me. And then we double fault, probably because either our interrupt table is invalid or the interrupt hand. Yeah, I think it's because probably the interrupt table is invalid here. So I do agree with the align 256 shit, which has to go somewhere. Here? How do we like align U32 align? This doesn't sound right. Can we not align an array? Zig align. Language reference. Okay, I want to specify an alignment though, not. Ooh. No. So I can do this. So if I go like U32 align 2v6. Oh, maybe I can't do it as. Maybe I need to do here. Ah. There we go. Okay. So we are still falling the fuck over here, and that doesn't happen if I don't write this in our vector table. Can we put the breakpoint here and just see where this goes? So we just jump straight to some random spot, which kind of makes sense, I guess. Now, if we set this interrupt vector table and we try to do the same experiment, we just immediately hit fucking. We just like go to 0, which seems bad. So it could be that we didn't set the right value here. It could be that this is offset by 1 or something. No. And then what happens if I put like, just don't initialize those at all? Does that change anything? No. So all of these are all just like immediately ripping to 0, which seems bad. Splat 0xff. Yeah, that's not a bad idea. Not a bad idea. Let's see if that does something else. So info registers program counter. Okay, so that's promising. Okay, yeah, so I think that this is doing what I want. So that's a good sign. So depending on what we put in here, we are ending up in that spot, right? If I drop this down to 4 Fs, I go next instruction, I'm at 4 Fs minus 1, right? So that's a good sign. So then the question becomes, why if I put why was it that when I assigned table 13 to be the thing that I wanted, did we not end up there? I guess maybe let's throw a 0 in there and see if that changes anything. Maybe 0x1234 was a bad number. So no. Okay, so where did we get 13 from? I don't know, because this should be 11. Okay, there we go. Okay, so that went to where I expected it to be. So I just made up that number. And so now if we go back and say SVC handler here, expected type U32, found pointer. Can we go like... So he can't evaluate that at comp time, which is interesting. So zig, like function pointer comp time. Like that's weird to me. Because maybe it's because that's like at link time or something. This just seems so strange. I was hoping that this would work. Because otherwise, I don't know what to do. I guess we could like create the table at runtime. It's just kind of silly. This is in the language reference. Like in the Zig language reference. Function pointer. Function bodies are comp time only types where function pointers may be runtime known. Saying deref, comp time deref. I don't know if that exists. I don't know what you're trying to say. But I guess for now, I can just initialize this shit at runtime. It doesn't really cause much of a problem, right? If we just go like this, and then we call init interrupt table. Raid message. My Rainer, thanks for the raid. What's up, you guys? We are working on... okay, we'll give you the whole story. I have an Xbox controller, right? It's a kind of third-party Xbox controller. He's got paddles on the back. The 2 paddles are remapped in the controller firmware to other face buttons, right? Which is kind of annoying because I would like them to be their own buttons, right? I plug this thing into a computer. I'm not an Xbox. I can support more than however many buttons are on an Xbox controller, right? Which is supported by like Linux kernel APIs and stuff. We could have real buttons if we wanted real buttons. We started looking at like reverse engineering the controller firmware. Seemed like a lot of work. And we're like, if we're going to do a lot of work, we might as well learn some, you know, real skills along the way for like real engineering. And so we're kind of on this saga to make our own Xbox controller, right? So make make our own PCB. I shouldn't say fab our own. We're gonna like ask some company to print a PCB for us, staple a Raspberry Pi Pico to it, and print an enclosure and have it send the correct signals over USB to our desktop so that it behaves like an Xbox controller. Boom. Now we can make as many paddles as we want. We can have the paddles emit whatever signal we want from the firmware. We control like the whole fucking shebang. And so we are in the middle of that saga. We are in the middle of trying to get USB support working on the Raspberry Pi. We are not using their SDK, which means that we have to poke and prod everything by hand. And in order to get USB up and running, we need to enable interrupts. So we're looking at how the fuck do you enable interrupts on ARM v6M. That's where we're at. So that's what we're looking at. Stick around if you want. But no big dealio if not. Okay, so you're saying that I can do pointers at comp time, but maybe am I just not allowed to do function pointers? Is that why it's mad? So you're saying that I can do like, or maybe if I write, like, do I have to write this as comp time here? No. Oh, fuck it. I'm just gonna initialize this thing at runtime. I don't know how to make this thing work at comp time. That's fine. It's fine. So this guy's just gonna work on the interrupt table that we have as a global variable. And he's gonna set this thing to the things that we care about. And then we shove that interrupt vector table here. Then when we call crash me, hopefully we end up in our interrupt handler. That would be kind of hype. So we go here, we go boom. Oh, let's fucking go, baby. That's so good for us. That's so good. So this should trigger some exception. We've had our SVC handler at that spot, and we hit a breakpoint there, which is hype. And so we're kind of hoping now that if we just do nothing and we set a breakpoint here, everything just continues to work. So we go next, next, next. We breakpoint back. That seems pretty promising, right? So I guess we probably want to confirm that the registers that we have before and after the interrupt are all correct. We want to make sure that we didn't like fuck up our stack or anything. So can we just like do some like stupid math in here? You know, var x equals 4, x plus equals 11, and then we say like var, you know, const y equals x, and then breakpoint or something. And then in here, we should start seeing that that like does stuff. I guess maybe it would be cool to like call some other function. And here we want to make this like an exported function so that it forces the C calling convention. And we just do this shit again. And so we should see some like heavy usage of shit now. Okay, so we get into crash me, we get into some other function, we have a backtrace that interestingly backtraces all the way through. That's kind of, I would not have expected GDB to handle this so well. But sure. So if we like disassemble the function we're in, we do see that we are using, you know, we are pushing registers onto the stack and shit. So we know that we've kind of touched stuff. And so I guess now all I want to do is I want to make sure that if I breakpoint kind of on either side of crash me, which I've already done, that everything looks the same. So here we are at 346 right before our crash. This is what our register table looks like. Continue till we get to 348. And we just want to make sure that these look the same. So bad news bears. R0, oh, I guess R0 is supposed to change actually. Maybe. Hold on. Okay. Let's go to crash me. And we'll just not do this part. Okay. Info registers. Continue. Continue. Info registers. So here, R0 did change between those, which is kind of surprising. I know that we're not like expecting them to get backed up, but I'd not disassemble. I'm kind of expecting crash me to have done nothing. Right? So why did anything change here is a little confusing to me. Unless breakpoint for some reason is changing register 0, I don't think it should be. Can we go instruction by instruction here? Info registers. R0 still like this. Okay, then we branch the link register. What in the fuck? Oh, that's weird. So they're just interspersing register loads here for some reason? Okay, I mean, that's kind of fucking annoying. But sure. So there's just some out of order execution happening here. So we can kind of fix this by doing a volatile right here, and then that shouldn't happen anymore. I'm a liar. It did. Interesting. Okay, whatever. It's fine. It's just loading the argument to the next function call. Yeah, I agree. It's just annoying to me that the breakpoints aren't going where I want them to go. I guess we can fix this by doing this in the assembly. If I put the breakpoint here, then it's going to be really fucking hard for it to, you know. We can't, Zig won't do anything to fuck us here. So here's our first one. Hello? I didn't save. It's hard life. Is this the new cursor update? No, surprisingly. Okay, so here, now things are looking the same. 100, 8, 0, C, 2385, 001, 1800, 203, some Fs, 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 Fs in the chat. This is all the same. This is all the same. 1F, some zeros. This program counter has moved, which is expected because we did move forward by one instruction. Everything else is looking the same. All right, cool. So that means that we're chilling there. We could also look at the stack of the interrupt side because we kind of expected that when we triggered our interrupt that, oh, we didn't actually, I'm a dumbass. We didn't run the interrupt. God damn it, dude. It's a hard life. God damn it. I'm a dumbass. Okay, info registers. Continue. Continue. Info registers. We have to do the check again because I'm a dumbass. Dump, 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 dump. All good. Doom, 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 doom. All good. Then a bunch of Fs. 1C401F. 04 has moved because the program counter's moved forward. Makes sense. Otherwise, everything's the same. Okay, cool. So that means that all of the like random shit we did in the interrupt handler did not have any effect on the registers, which is good. That means that the interrupt handler is, as we expect, backing up the registers that it needs to. So having just a raw normal function here is like probably okay. Why not C? Just asking. Zig is better is an answer. It's like, I say it as Zig is to C as Rust is to C++. I think the Rust people don't like me saying, or the Zig people don't like me saying that. But That's how I feel. It's like a kind of like modern, like, version of what C could be if you, it's like what C could be if you brought it into the future, is how I look at it. And I tried it and one time and I liked it, and now I just keep using it. It's kind of about the extent of it. Does the interrupt handler back up the registers to the stack? So my understanding is that the typical ARM calling convention is that functions back up the registers themselves, right? So if we look at the disassembly of the SVC handler that we wrote, okay, maybe we do this. Backtrace, disassemble like this. No, up. We just assemble like this. So like this guy, he internally says, hey, I'm going to use R7 and the link register, so I'll back that shit up. Although he is just using R0 and R1 and R2 willy-nilly. And he didn't back those up at all. So I guess that means that the exception handling is doing that for us, right? I think we saw in the ARM spec somewhere, they have exception entry behavior. Wait, so it's Zig, not assembly. We're kind of flip-flopping between the two. Oh, and then you're saying why assembly over C is because I want like just raw control of what instructions are generated in some points. Okay, so when pushing context, hardware decrements the stack pointer to the end of the new stack frame. When popping, hardware reads data back. When pushing context to the stack, the hardware saves 8 32-bit words. Aha, okay. So they are kind of saying when we back ourselves up, we are, since R0, 1, 2, and 3 are expected to be scratch registers, because of that, then they back those up in the exception handler, I think. Yeah, subroutines must preserve the contents of R4 to R11 and the stack pointer, right? So because of the fact that they're kind of saying like, we're trying to make it so that you can just call a regular fucking function here, and we'll back up the things that you wouldn't normally have backed up. That seems pretty reasonable, right? So this function is just fucking raw slamming stuff into R0, R1, R2, but who cares? And then if we put the stack pointer here, we should be seeing that's like something relatively close to 2004, which we are because he has switched stacks for the interrupt handler, which is pretty sick. Okay, I think all this makes sense. So they just preserve the stuff that they need to, and then we're chilling. Cool. So I guess we kind of did everything we wanted to, huh? I guess probably the next steps are to try to get an external interrupt from a GPIO or something. But at the very least, populating the interrupt table was not really that hard at all. We're an hour and 15 minutes in, but all we really did was like write this register. That's kind of the extent of what we had to do. And we just said, yo, here's some handler. Boom. Hype. Okay. So the question is do I feel like I have enough context here to keep going and do the GPIO stuff? I think we kind of pivoted. So I think we got some time. Okay, let's try to make it so that we trigger an interrupt. Trigger an interrupt on GPIO. Let's try that next. As far as I know, registers are pushed and popped from the function prologue and epilogue, respectively, and the compiler generates the instructions for those. That's for x86, though. Does the hardware do it on ARM? So I think that what's happening here is that the compiler will generate prologues that will back up any registers that it uses in the range of R4 to R11, right? Then the hardware on exception is pushing the rest of them. Right? So he's saying that, like, yo, we agreed, the calling convention agrees that when I call a function, I expect R0 to R3 to get clobbered. But when an exception happens, that can't happen to me because, like, I can't provision for exceptions to be called between every single instruction. Right? So then the hardware is saying, we'll save some extra shit for you. Kind of my understanding. And then my understanding was also that on x86, it's caller save, not callee save. But maybe I'm wrong. This really is important. Yeah, so here, oh, this is for passing parameters. Then they save old frame pointer, reserve stack space. Not sure. Doesn't matter though. Doesn't matter. Okay. Let's try to enable gpio interrupts. So I think we were looking at the RP2040, the system on a chip. He has a section on GPIOs, and in there, I think that they had an interrupt segment. So it's just that we write to the dormant wake register, I believe, somewhere. Shouldn't callconf naked prevent those function prologues? Yes, but I think we're not trying to avoid them. I don't think. I think we want them. Okay, so there are enable, status, and force registers for 3 interrupt destinations. I assume force just means, like, trigger an interrupt. What does the force thing do? Because if we can just write that, then that gives us something to test with. Software examples, enable a GPIO interrupt. But this is with their SDK. Yeah, I mean, I assume enable, status, and force. Okay, so level interrupts are not latched, blah, blah, blah. So this is interrupt enable for this pin. This is interrupt status and force. Okay. But then this is not what we saw. We saw something about, like, dormant wake. Dormant wake is used to wake the ROSC and XOSC up from dormant mode. Oh, I see. Which we probably don't care because we won't be in dormant mode. We're not sleeping or we're not, like, turning off our clocks or anything. So that should be fine. So, okay, what is their SDK do on GPIO interrupt initialization? So they call set IRQ enabled, which they just set bits for they take the address of dormant wake control. Then from there, they offset by inti or something. What is this? What is this type? Oh, so this is inti, intf, and intis. Inti, as well as... What the fuck is going on here? I don't know what the fuck this means. But they're looking for something that has an inti, intf, and intis. Right? So that's kind of what they're talking about here. Inti, intf, and intis. Inti... Oh, but these are like... what am I missing here? So this is, oh, there's 4 of each of them. 4. Why? Oh, for maybe I see. Okay, so they have inters. Then they have int e 0, int e 1, int e 2, and int e 3. I see. So then it's these inties, then the int f's, then the int s's. Okay, so that's what this is supposed to be. Now I don't know why the fuck they are passing in the address of dormant wake control 0. This is weird. That seems strange to me. I guess these things are offset from somewhere. I see. So they're like offset from, they're using these IO banks, I guess, have interrupt sets for processor 0, processor 1, and the dormant wake control. Right? So we're seeing, I see. So they have dormant wake here, int 0, int f0, int s. Then they have proc 1 and proc 0. So we probably are chill to just use the proc 0 ones for now because we're not sleeping the processor ever, would be my assumption. Then they call this, I see, with this guy. Nice. Okay, I think that makes sense. Where was I seeing dormant wake control? With set dormant IRQ enabled. I see. So I think we're chilling. So we need these definitions of int e, int f, and int s. But probably we can get away with int f for a second. Right? I assume when they say force, that means just like fucking run that shit, right? Force. Do they talk about what this thing means? No, they just say like, they just use the letters. Cool. But I think it's reasonable to assume. I think. I mean, also, I guess it's not hard to just trigger this shit ourselves. So maybe we can do that. Okay, cool. So let's find these interrupts. Fuck, I lost it. Int e. GPIO. Interrupts. List of registers. Okay. So we want processor 0 interrupt enable. Okay, yeah. Which is at offset 100 from IO bank base. Okay, so here we have IO bank 0, and we should be able to be like GPIO interrupt enable takes in an interrupt number, a GPIO number, and we'll turn a registers GPIO interrupt. No, this is just like this. Interrupt enable registers GPIO interrupt enable initialized with base plus 100. And I guess this is interrupt enable 0, 1, 2, 3. And these are actually proc, the processor 0. These only trigger on the first processor. Why are there 4 of these? Oh, I guess because there's 4 interrupts. So the GPIO, we only need 1 of these. Yeah. And then are all of these guys just like the same fucking mask? Edge high, edge low. Oh, wait, no, I'm seeing it. So they're split because we need 4 registers because each of these guys have edges and level. Right, so we go back to offset 100. Yeah, so we need 100 down to like FC, F8, F4, FO. So we need all of these. So this is like this. Then the last is 0, 1, 2, 3. This was F4, then F8, FC. Oh my god, I'm a dumbass. 100. Sorry. The first one, we want proc 0, interrupt enable 0. God damn it, dude. So it's 100, 104, 108, and 10C. There we go. Yes. Okay. God damn. You probably want the naked functions, otherwise you have to do some sort of inline assembly to do it yourself. But I think that like my understanding, sorry, I know you said this a while ago, but my understanding at this point is that I don't need any specific preamble on ARM because of the fact that the processor is backing up any of the registers that I wouldn't naturally back up. So I think it's fine. I think. Can you explain why you have multiple files in different languages? I'm kind of a beginner. Oh, it's just because like there are some things that are too low level for a low level language like C or Zig. So dropping to assembly is like fine. Worth doing. Okay, let's make our register definition for whatever the fuck this thing is called. GPIO interrupt enable. So here we have some register fields, and I guess each of these is an individual bit. Yeah. So, that actually means that we want different types for the different options as well. We want like 0, 1, 2, and 3 to all kind of specify which GPIOs that they are allowed to interact with. And so I guess that means that we're gonna do some like Vim macro shit. Because I do want to be able to access these by name. So this is for number 0. Okay. So what are we gonna do? We're gonna say go a couple words forward, delete. Do that a few times. Okay. Then we're gonna say take this thing, bring it back here, and then put it in quotes, and then put a comma at the end. Okay, that's looking good. Then in here, we're gonna go lowercase this shit, please. Okay, cool. And then I think this copy pastes nicely into this. Oops. Yeah. Cool. And then maybe we will only do the first one, because I don't want to do the rest. And then I suspect that these are going to be the same for the force and status. So I suspect that we can kind of reuse this type. So interrupt force 0 is going to be 110. And then status 0 is 120. And it does look like they're the same. Okay. So now we should be able to be like... GPIO, I guess after GPIO initialization... let's look at the pinout here, I guess. And where is our pinout? Raspberry Pi Pico pinout. Nope. Here. Okay, so we are this guy. So say we want gpio 20. Which one of these is like easily identifiable? 26 or 29, 22 lines up with the bottom of the SOC. I can easily see that one. Okay, so we'll say, let's use gpio 22. So we're gonna be like init gpio 22 here. We're gonna set the LED as an input, which means that I guess maybe init gpio input here. We probably have to be careful with the type here. Probably this thing needs to be like a U5 or something. Then we use gpio here, but then we don't want this thing to be an output. We want this to be an input. So probably this like output enable set is wrong. We can like reference what they do in the SDK, I guess. Init gpio init maybe? Yeah, okay. So they set dir to in. Where do they define that? Am I stupid? Oh, here I see it's inlined here. So they set if we are a 2040, which we are, then they call this, which just sets output enable clear. Okay. So I guess we need OE clear, probably, which is offset 28. So we clear this guy. We probably don't have to initialize this value, and then we just say use this thing as GPIO. Cool. And then how do we like read the value? We've never done that before. So we just have a GPIO in register, which is just this. Okay. So this should just be like this. Okay. So, and then we want to set this guy as pulled up by default. So how do we do that? We've done this before, maybe on UART? No. I2C? I swear we've done pull-ups before. Init I2C master, here it would be. This is where it would be. So we set this guy like this. Okay. So here we say input enable, pull up enable, pull down off. We probably don't care about these. Seems reasonable. So set as an input, set as a pull up, call it a day. Then I should be able to read the GPIO in value and see what it says. It should be up by default. So we say like init GPIO input on, what do we say the number we wanted was? 22. And then we look at the GPIO in. we should be able to see this guy set the value to high. We should see a 1 on GPIO 22 here. He's mad. What is the rate the controller talks with the computer? How do the joystick signal get to it with a continuous signal or just the position once the joystick is sent once? I think my understanding is that every time the joystick moves, we're supposed to send to the computer. That's my understanding. Could be wrong, though. Where the fuck are we? What the fuck? Oh, yeah, that's right. So we like print as a Boolean GPIO val, or sorry, print as binary GPIO val. And we look for this and 1 shifted by 22. This is set. So that's good. That means that our pull up is working and we're reading. And if we set this to pull down instead, we should see that as 0. And 1 shifted by 22. 0. Nice. Nice. Okay, so that means that's working. And so now we can run this again with pull up enabled. So it should be 1 by default. GPIO val and 1 shifted by 22. That's set. So now what I want to see is if I hold that pin to ground and reset. Oopsies, I just fucking reset the whole processor. Got to be careful with that one. I probably need to do monitor reset init. Hold this on the right pin. Hit enter. Continue while holding on that pin. It's kind of hard to hold this and type. Okay, so now it was 0. Okay, so that's really good. That means that when I touch the pin to ground, we are seeing the value change. So now we should be able to enable interrupts on that pin and trigger a reset. That's what I'm kind of hoping for. So did we set that up already? It was like proc 0, interrupt enable. Yeah. Okay. But I'm a dumbass, and 26 is not one of the pins that I can work with on proc 0. So can we change this to like maybe pin 4? Maybe pin 4 is a better one, because we can change that. So let's just do the same test here. So P GPIO val 0, 1, 2, 3, 4, that is set. I want to hold on pin 4 now, which I believe is 4 was a bad one. I should have done 2. I'm a dumbass. 2. Okay, PT GPIO val pin 2 is set right here. And then I ground that guy, which is the 4th pin here, and I do monitor reset init, pre-jack SC, hold the button down, ground it, hit enter, and then this guy 0, 1, 2, he's still set. That's not good. Maybe I didn't ground it good. That's not good. That's not good at all. I don't understand. Maybe I'm missing? I am. I was clicking on the wrong one. I'm a dumbass. I'm a dumbass. I'll admit it. Monitor reset init. Continue. Print. Now it's grounded. Nice. Okay. So all of that now to say that we should be able to go like IO bank 0, processor 0, enable on this guy. Maybe we do like atomic right. Is that atomic set? We have some function for this. Yeah, okay. And then we atomic set this with 1 shifted by 2. So that should say enable interrupts on that guy, except that's the wrong value. I'm just a dumbass. We want modify here. And in modify, what do we have? It's like gpio mask. Hold on. We added like that gpio mask thing, and we have gpio for edge low. gpio for edge low. Just turn that shit on. Like that. Okay, and then what we are hoping to see is that when I ground that motherfucker, our program just like fucking crashes. So I like ground this shit. And nothing is happening. Which is a little disappointing. Let me breakpoint at the beginning again. Okay, so I hit the breakpoint, hit continue, try to ground this shit. And yeah, nothing's happening. Which seems bad. That likely means that there's more to enabling interrupts than this. I think they had an example program in here somewhere. Do I have clang tools here? I do. Let me just get into an environment that has jump to definition and shit for C. So they have an example using their SDK of how this shit's supposed to work. And so I'm kind of hoping that if we just look at that example, maybe we'll get lucky. Okay. So all he does is he does initialize the GPIO and then set IRQ enabled with callback, which is not resolving here the way I want it to. Okay, so this says set the callback. We don't have to worry about that part, I don't think. Then they just set the IRQ as enabled, which calls, you know, depending on my processor, I set hardware bits on the enable register, which was int e over 8. And then this is 4 times GPIO %8. Oh, so he's enabling on all 4, which I guess makes sense. We could try that, right? So we can do like GPIO, we can do like a combine. I think it's like this is the way that the syntax worked out. Edge high, edge low, level high, and level low. Right? They're kind of just enabling. Oh no. Wait, what are they doing here? Four times events. Oh, I see. So they're allowing the mask. Never mind. They're not doing that. I'm a dumbass. So let's just leave this the way that we had it. We want it to trigger on edge low. And then the only other thing that they're doing that we're not is, where the fuck were we? Hello? Was they were clearing the interrupts. They were clearing out anything on the interrupt field here, which was on the IO bank. Okay, so IO bank 0, enter. We should just like write this to 0 or something, right? Something like that. I think. So this is, I think, yeah. So they should just have like a IO bank 0 enter or something. how do they call this? IO bank 0 base or something? Here we go. And then on here, there should be an enter field here. And so enter 0 is the guy. So we actually have like the same shit, I think, where we have I think it's just enter 0 is wherever the fuck this guy is, F0. Right? And so here we're kind of hoping to see that we want to write to this guy to clear him. Am I high? Enter 0. We're just clearing this fucker out. Then we... Yeah, okay, this makes sense so far. And then maybe down here, every iteration of our loop, we'll just kind of read the interrupt status. And then we should be able to print this later. Yes. So that will let us know if the interrupt fired and we didn't catch it in the CPU, or if the interrupt just never fired. Both of those are options. Okay. So program is running. I tap this shit, hit breakpoint, and then go up. That's interesting. So somewhere we must have to enable something else. So let's just let me run this one more time. So if we print this value again, we print enter status 0, 1, 2. So that is set. That's a little annoying. I would have assumed that we cleared out interrupt 2. Wait, which GPIO are we working with? We are working with GPIO 4, GPIO 2 on pin 4. And enter 0 is this. What format is this? Sorry, my brain, it's falling over. I can't, there's too much stuff happening. Oh. This interrupt status is a lot of stuff. So we actually want to look at 16, 17, 18, and 19. My bad. My bad. Okay. So we want GPIO 2, level low and level high. So we want, and then we want write to clear on edge low and edge high. I think I understand. So first of all, our write clear means that we should be writing 1s here, not 0, to clear all our interrupts. Then we reset this shit, hit continue, breakpoint, go up a level, print interrupt status as this, and then can we mask off with 8, 9, 10, 11? Maybe we just shift right by 8. So 8, 9, 10, 11. So we are level high and with no interrupts fired, right? That's what we're seeing here, I think. Then I tap this motherfucker. Just tap that shit. And then breakpoint again. Hype. So now we have seen edge low. We now are high again, but we've seen both edge triggered now on this pin. Okay, so that's good. Now the question is why the fuck didn't that do anything? Right? Like, the interrupt register on this GPio controller is doing shit, but like maybe the external interrupt mask needs to be set. Right? So we might have here that we have interrupts for IO bank 0. This seems likely to need to be turned on, right? So we need to, I assume that it's this guy, right? It's gotta be. And so somewhere we must have to enable that shit, right? That just seems like the type of shit they do, where we have like interrupt mask or something. Interrupt mask. This is for UART, so maybe not. So I also wanted to look at NVIC. Seems like a word. Oh, here we go. So there's priority levels as well as masks. Yes. The NMI mask for each core can be configured with this guy. Yeah. Each one of these registers has 1 bit for each system interrupt, and each core's NMI is asserted if the system interrupted is asserted and the corresponding NMI bit is set for that core. So I guess we should look at this. Zero. So if we were to do like, what was it, 13? Yeah, 13. Then I tap that shit again. No dice. But also the interrupts weren't cleared. So maybe we're not that lucky. Okay, so can we do, I don't know, sysconfig, what the fuck was this called? NMI mask or something. Let's just do this for now. So we shift this left by 13. Boom. Turn that shit on. Build. He's not happy because this needs to be a pointer from int here. Okay. Run that shit. I'm gonna unplug replug actually, because I want to make sure that like, you know, we haven't like left anything over from previous runs. Okay, and then I tap that shit. And nothing fucking happened. That's annoying. I would have thought that that was it. So we are missing something. Proc 0, NMI mask is offset 0. What happens if we just get crazy here? We just set them all. Let's just get fucking crazy out here. Still tapping that shit is doing jack shit. Okay, so it's more than this. IRQ. This sounds interesting. So this is on pin IO. So we're saying, so just to confirm again, if we write the interstatus up here, right before our breakpoint, we should see, we want to see that the interrupt for pin 2 is not fired. So we shifted this by 8, right? So we're looking at this bit here, right? We continue, breakpoint, up, and we print this again, still unset. Then I continue, tap that shit. Okay. Then up. And these guys are now set. So we do have confirmation that we have cleared the interrupt flags at the start of the program. We run it. And when we hit the thing, then we see those fire, right? But we don't see them make it to the CPU. So why? Why? It could be some pin is in reset that's not supposed to be. Could be that we haven't configured this thing correctly. Likely that. It's likely that. Fuck. So it could also be that the interrupt table is maybe getting mad if like we've kind of initialized the interrupt table with zeros. I wonder if we like initialize this thing with Fs, if like it'll behave differently. Maybe it checks, you know, if the interrupt handler is set or not. No, not so lucky. Not so lucky. Okay. Okay. So supports for both level sensitive and pulse sensitive interrupt lines. Wake up controller. So I guess somewhere we have to configure this guy for like, hey, I want you to tell me if like, you know, interrupt 13 goes crazy, right? So maybe we can look at registers associated with this guy. External interrupts are connected to this guy. He prioritizes interrupts, blah, blah, blah. We have these registers. So here, we probably need to enable these, right? If a pending interrupt is enabled, yeah, this looks promising. So what did we change? We enabled sysconfig NMI mask, which is not this. What the fuck is sysconfig then? I guess non-maskable is different. Okay, so we'll go back to wherever the fuck we were a second ago. This guy. nvic isser. Baby. So here we were working on Cortex M0 plus nvic isser. And this is at this address. And we need to define this guy. So nvic isser interrupt service enable or something register maybe. Oh, this guy doesn't need a definition. He's literally just a bit mask. So we're gonna do like pointer from int of this. Okay. So now we want to do like, first let's read this thing. Okay. Let's just see what that looks like right now. He's mad because probably I fucked up and didn't save here. Nice. Okay. So this is like, everything is off. If a pending interrupt is enabled, so how Then we have clear enable and forces interrupt to the pending state and clear pending. Okay. So what if we just are like, what if we got crazy? We're like, just set everything. Maybe. I think that that might actually be triggering the interrupt. It's actually kind of hard to tell. It's a little hard to tell, but he doesn't like this for sure. So can we just do like 1 shift left by 13 or something instead to try to enable the only thing we care about? Okay, so then I tap that shit. Unlucky. Determines which interrupts are currently enabled. If a pending interrupt is enabled, the NVIC activates the interrupt based on its priority. So I assume that this is right. This is what I want. Somebody's linking something. Configure the vector table, initialize NVIC. So here they're like, enable this thing with some priority. And then they set the interrupt routine. Yeah, so it's not really... They're not going too crazy. They're not going too crazy. So let me double check that interrupt 13 is the one I want. I guess it's 13 plus the offset. Right? It was, like they said... I think that they said that external interrupts are after 16 is something that we saw somewhere. Right, because these are all external interrupts, and we saw in this document that external interrupts are offset from 16. So we could try that. It is 13 is the one we want, right? 13 is IRQ bank 0. Yeah, that sounds right. Okay, let's try that. Tap that shit. No dice. No dice. Okay. So the 26 system IRQ signals are masked via NMI mask, then ORed together, creating the NMI signal for the core. So we have these sysconfig registers. So we set the sysconfig, we said, oh, maybe mask is bad? Maybe mask means don't use? That's a possibility. No dice. Allow me to interrupt. Thank you. Good one. Fuck. So, is this thing, like, what does this mean? Each of these registers has 1 bit for each system interrupt, and each core's MI is asserted if a system interrupt is asserted and the mask bit is set. Okay. So we do want these to be set to fire the interrupt, I think. I wonder if we can look at the SDK use of, like, do they have, like, NVIC in here anywhere? You know, like, do they initialize this shit? IRQ here. So here, IRQ is enabled if... Okay, they have an NVIC ISR, which we have, I think. IRQ set enabled. Okay, and then do they have, like, maybe some sort of, like, global initialization for their interrupt stuff? Let's see, let's see. I don't see anything. I remember that, so clocks in it. I remember being confused about the fact that this was never called anywhere. Yeah, I'm confused again. I remember them having some way to like inject functions that run when the system comes up. How did they do that? It was something about like weak function declarations, runtime init. Okay, this sounds familiar. Yeah, okay, so they had something about like runtime init in here, and they runtime run initializers, which comes from init array. That which they put stuff into the init array section. And this stuff runs at startup. How the fuck do they do that? A lot of STM shit in here. Is there like... God damn it, dude. Why do they have to make everything so complicated? Why you gotta make things so complicated? Ba-dum-bum-bum-bum. Fuck, man. Where I remember seeing it in like Watchdog in it as well, being Watchdog. Init Watchdog? Fuck. I can't remember how we got here before. We found it at some point. I just can't remember how. Okay. Pre-init array? Like, where are these guys coming from? Pre-init array start. Oh, these are like... Oh, wait, what's in here? This seems... Pico... This is it. This is the one. Pico, runtime, init, func. And we were going to look for any of these in IRQ. Nice. Runtime, init, per core priorities. Nice. This is exactly what I was looking for. Pico, runtime init. So is this the only thing that they do on runtime init? It looks like it. Okay, so what is happening here? They're going in here and they're saying, Jesus Christ. So they're iterating over all of the priority guys and setting it to what looks to be some sort of like bit mask. So maybe we should be looking at those priority registers. Okay. So so they're like, yo, 0 is the highest priority, 3 is lowest. Writing 1 does not affect the active state. These registers are only word accessible. And here they're just like, why do we have to write these? What am I looking at? So they have the default priority, which is 0x80. And they're multiplying that by set this on every 8th bit. Yeah? Or something? So I see. So these guys are, or every, oh, this is hex. Yeah, this seems like every 8th. So they have 8, 16, 24, 32. Yeah, okay, that makes sense. So they're just setting all of these guys to low priority. I think that's what they're doing. Yeah. And their reset value is 0, which seems like it should be fine because 0 is just higher priority. So I don't really think this should matter. Okay, then they have like, when you set enabled, they just call, they set cpio and isr. So clear pending. So they say clear any interrupts that happen to be left over. And then they also enable it according to the mask. Okay. Won't this be a problem where they're turning off other guys? Maybe it's fine. So are we doing that? ICPR and ISER. Ah. So this guy, we need to make sure that to disable interrupts and determine which interrupts are clear. So they are, the fuck are they doing? Oh, ICPR, not ICER. ICPR. So this is clear pending interrupts, which we probably are not doing. So there might be some interrupts left over. This thing might initialize to like fully, you know, it might be that like the interrupt has fired at some point in the past and we don't know how to deal with, like, it won't trigger until we clear it. So they clear the interrupt for the thing that they're about to turn off. But then otherwise, that's kind of it. Maybe. It would be nice. That's fine. Let's just see. Still nada. Still nada. Wait. ICPR. Is that what I did? ICPR. ICPR. Yeah. Removes pending state and interrupt. So I guess we could read this guy and see if he thinks it's pending. That might be interesting. Var ICPR status. And we do this every frame. Then we could see if it triggers. So here we breakpoint up, ICPR status. Oh, that's interesting. So here we think we should be at 1 shifted by 13. 0 or 1 shifted left by 16 plus 13. Is that what we think right now? Is 16 plus 13 less than 32? Yes. Okay. So then I hit continue. I slap this shit. And we go up. And we print this same shit. Okay. So neither. That makes sense. So the question becomes is, are we doing this wrong? Who fucking knows, dude? Who fucking knows? All right, not sure. I'm gonna do some more reading. Call it for the day. Unfortunately, we did not succeed in getting this part up and running, but we did succeed in getting interrupt handlers working in general, right? So we did prove that we can set an interrupt table and work and trigger it with the use of this instruction, and we confirmed that we were like returning from those interrupt handlers. Okay, our only problem is now that we are struggling with external interrupts, but we're just missing something. But I can't go forever, so I'm gonna call it a day there, do some more research. Maybe I'll try some more tonight. I don't know. But that's it for today. So thanks for watching, guys. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 4:30 now, so anywhere between 4 hours ago and half an hour ago is when you should expect to see us live. We're kind of on this saga right now of creating an Xbox controller, so we're going to be touching on a lot of stuff like embedded programming, drivers, 3D printing, PCB design. There's a lot of this stuff that I'm not really familiar with and don't know how to do, but that's part of the fun. So if you want to watch me bumble through that, swing back by. There's a lot of other projects on the YouTube as well if you want to look through the backlog. Otherwise, I guess the stream is typically segmented into two portions. There's kind of the happy hour portion, we call it, which is kind of like unstructured. Today we were doing a bunch of the research that we need to do to get USB up and running. And then there's kind of like the main segment, which is what you're seeing right now. Only the main segment gets put onto YouTube. So if you want to see the rest of the stuff, you either have to catch it live or subscribe on Patreon or Twitch to see the VODs, or join on YouTube to see the member VOD section. The reason that these are segmented that way is because, this stream will end someday, right? And if you want this stuff to continue, this gives you an incentive to throw me some money, right? The stream will end when I run out of money. And so every dollar I make doing this extends the lifetime of the stream by some amount. So if you want that stuff and you add access to the secondary VOD segments, feel free to contribute in whatever way. But if not, no big deal. I think that's all the plugging and chugging we got to do. YouTube, peace out, and Twitch, let's find someone to raid.